Let us start this lecture with a thought process from Rudyard Kipling, who feels that I keep 6 honest serving men. They taught me all I knew. Their names are what, why, and when, how, and where, and who. Okay. So, these I consider like all these, what, why, when, how, where, and who are basically 5 Pandavas and Draupadi. You can identify who is Draupadi. Okay. You can think about that. And let us, before embarking into the new topic or the new thing in this lecture, what we will be doing, we will be trying to recall what we learned in the last lecture. Can anybody tell me? We started the discussion on basically about various forms of energy, and energy is very important. So far the thermodynamic is concerned, right? And so we looked at both microscopic forms of energy and macroscopic forms of energy. And macroscopic form of energy which we will be interested in, right, and we will be working on that, but the microscopic energy is more important, because we will be utilizing this microscopic forms of energy, which is also known as the unorganized form of energy. Am I right? This is not organized properly. And the task of thermodynamic is basically to convert this unorganized form of energy into organized form of energy, so that we can utilize for our purpose, in engineering applications, right. And after that, we moved into a concept known as what you call equilibrium, right. And I took an example of connecting a copper rod to a hot bath, that is something hot water bath, which will be maintained at a constant temperature around 100 degrees Celsius, right, and the ice bath we connect. So, if you look at both are connected on both the side of the copper rod, and we consider the copper rod as our system. Am I right? We allow a lot of time to heat transfer to take place from the hot water bath to the cold water bath. And then you people told me, look, it has attained, the copper rod is attained the equilibrium. Actually, it is not. It was attaining what? Steady state, right, but not equilibrium. When I isolated that copper bar from both the baths, which are basically surrounding, right, and this is the system, copper rod was the system, and the hot water bath and the cold water bath as the surrounding, and isolated and insulated also, then it attains a temperature, right, and that temperature means there is no gradient in the system. Which is your system? This is the copper rod is your system of gradient of temperature. Therefore, we call it as a basically reach a equilibrium. Today, we will be continuing to discuss on that what you call the equilibrium things, and question arises, what do you mean by thermodynamic equilibrium? That means, when a system will attain the equilibrium in thermodynamic sense, right. So, let us take an example, right. What we will do? We will take a copper rod, that is the what you call the first one, copper 1, So, this is your copper rod 1, which is at 0 degree Celsius with a partition, this color is partition, with another copper block which is at 30 degree Celsius, right. Now, both are separated such that no heat is transfer taking place, although the temperature gradient is there. One is at higher temperature, other is at lower temperature. Now, I will remove this partition, right. and then of course, both will be come in contact, you can assume that way, or you can assume this partition is very very thin, right. And then there will be some heat transfer, and this is that became our system, what you call, this will be my system, right. And then I allow for a longer period of time. So, what will happen? Some heat will transfer from higher temperature to the lower temperature, because that is the way how heat transfer from higher, I mean gradient, right. So, after reach if you give a sufficient amount of time, this whole system, right, it will be basically, if you could look at, this is my system, and that will be attaining a temperature 50 degrees Celsius. Like if you look at, there is no gradient in this system, I mean this is my system, and in that there is no temperature gradient, it is all uniform, that, and that we call as a what you call a system as reach a equilibrium state, right. But is it thermodynamical equilibrium? No, it is not. Actually, it is thermally equilibrium, right. We call it as thermal equilibrium, because the uniform temperature is attained, right. But thermodynamic equilibrium will be having a very what you call a wider connotation, right. That means, there will be various gradient will be there, right. There might be pressure gradient, there might be concentration gradient, there might be phase change, kind of things. So, therefore, a system can be said to attain a thermodynamic equilibrium only when it attains not only the thermal equilibrium, but the mechanical equilibrium, chemical equilibrium and phase equilibrium, right. So, these are the things we it must be satisfied, then only you can call a system to attain equilibrium thermodynamically. So, therefore, one has to be little careful, and let us understand what we mean by mechanical equilibrium. We will take a what you call a piston cylinder arrangement, in which we will be taking a gas, and this is our system, right. This is our system, and to start with, this pressure acted by the gas on this piston, this is our piston, okay, and will same as that what is being applied on the other side of the piston. So, it is in equilibrium, right. For example, if I will increase the pressure, let us say with delta P, what will happen? What will happen? The change in pressure is there on the this P2 side, that means piston will be trying to push the gas, right. How long it will go on? Till it attains another equilibrium. For example, like in this case, that piston can move to in this place, let us say piston become moving to this one. So, that this gas will attain another pressure, which will be same as that of the P2, and P2 is increased by delta P. Then it will attain another equilibrium, that means, all those molecule here, right, will be having the same pressure in the system. Are you getting my point? Yes or no? But that will happen under what condition? One has to. For example, I will increase this pressure, is let us say if it is to start with 1 atmosphere pressure, I will give another atmosphere pressure, 2 atmosphere pressure at the P2. Will it happen or not? Think about it. But what you can understand at this moment, that if the system attains the uniform pressure after a change, right, there is no gradient in the system itself, then it has attained a mechanical equilibrium, right. So, therefore, the equality of pressure you can say it is, whenever a system attains equality of pressure across the thing, across the all the domain of the system, then we call it as a mechanical equilibrium. Now, let us take another example, right, of chemical equilibrium, and chemical equilibrium like depends upon what? Basically based on concentration. For example, suppose I am using some perfume right here, I have just come suddenly, and can you smell it? If there is a perfume here is being there as spray here, and after some times you could smell it, right. How? Because the molecule of the perfumes have traveled, although there is no velocity in this room, right. It is going because of concentration gradient, right, that we call it as a diffusion. So, and let us take a similar example what we had taken earlier. These are two chambers, one is containing oxygen, right, the first chamber which is at 300 Kelvin and 0.1 megapascals, and it is this chamber, the first chamber is separated by another chamber which contains nitrogen gas at 0.1 megapascal and 300 Kelvin, right, and there is a partition here. And what we will do? We will remove this partition, right, and then what will happen? Oxygen will be trying to move in this direction, right, and nitrogen will be moving in the opposite direction, because it is concentration of nitrogen is 0 here and here it is very high. So, therefore, it will be moving towards that, and this will be after certain time what will happen? What will happen to the concentration of oxygen and nitrogen? It will be uniform across the whole system. If I say this is my systems, this is my system, right. So, across everywhere it will be uniform, provided you have given enough time for the diffusion to take place, right. And as a result, the change in concentration will be 0 in the system, there will not be any change, concentration is uniform. So, then we call a system has attained chemical equilibrium, right. I mean, this is a simple example I have taken, but let us consider another example where 2 moles of hydrogen is mixed with 1 mole of oxygen, right. What will happen? It will be mixed properly. Let us say all diffusion have taken place mixed, and if it will attain a high temperature, then what will happen? It will go to 2 moles of water, right. And at the same time, the water can be converted into oxygen and hydrogen as well, both will be simultaneously taking place. That means, the hydrogen is reacting with oxygen going to the water, and so also water can be dissociated to the hydrogen and oxygen, provided it will be at a higher temperature, otherwise no. Okay. So, now we can call basically there will be forward reaction rate and there will be backward reaction rate, because chemical reaction is occurring and there will be formation of new bond and also breaking of bonds of this thing. So, all these things going on, and then it will attain a equilibrium only when this forward rate of reaction is equal to the backward rate of reaction, then system attains a chemical equilibrium, right. So, if you and similarly it will be happening like whenever let us say you are boiling water, what will be happening? The water at a particular pressure and of course, at the boiling point 100 degrees Celsius for atmospheric pressure, that will be what you call remaining constant, and there will be change of the water vapor will be converted into water will be converted into its vapor, and some of the vapor may be coming back to the water and it has reached a equilibrium, and that we call it as a phase equilibrium. So, to summarize that what is the thing, that means a thermodynamic equilibrium can only take place if all these 4 equilibrium, that is those are like thermal equilibrium, mechanical equilibrium, chemical equilibrium and phase equilibrium are being satisfied. In other words, a system can attain equilibrium thermodynamically if all these 4 equilibrium can be attained by it. If you look at thermal equilibrium, basically equality of temperature, and mechanical equilibrium, equality of pressure in the system. Whenever I am saying, it is basically equality of pressure, and the chemical equilibrium is basically equality of concentration, right, and phase equilibrium is the equality of mass across the phase boundary. That means, whatever the let us say solid to the liquid or liquid to the solid can be, the mass will be same, remaining same. So, therefore, it will be the phase equilibrium. Now, we will look at like how stable is the equilibrium, right, that part we will have to look at it. So, that means this equilibrium states is there, but it may be stable, it can be unstable, right, or it can be neutrally stable, it can be metastable. So, the stability is very important part, like if you look at equilibrium state can be divided into 4 categories. One is stable equilibrium, neutral equilibrium, unstable equilibrium and metastable equilibrium, right. So, let us take a very simple example which most of you might have aware that let us say there is a ball which is here in a curved surface, and if this ball due to something will move to let us say this place, what will happen? Ball has due to some force it has gone to this place. After certain time what will happen? When the force is released, what will happen to that? Ball will be returning back to this position and it will stay. Similarly, if there is a change in the position of the ball in the other direction, right, then again ball will come back and stay in the minimum energy state, right. If and under this condition we call it that it has reached a stable equilibrium, because if there is a change of the position of the ball, it can return back to the undisturbed position, right. It does happen in our life, am I right? Suppose somebody will scold at you, right, your mind will be agitated, am I right? Yes or no? Somebody can praise you, you will be elated, and then after that you will come to your normal position, right. That is nothing but your stable equilibrium. Either you are happy or you are unhappy, your mind will be agitated, right. You are not in normal position, stable position. So, that is the natural we do experience, and which we will be basically looking at kind of things. And let us look at another example, what we call as a neutral equilibrium. Suppose this ball is there in a flat surface, ball, and now due to some force will be acting, there will be some change in position. So, let us say ball will be coming over here, depending on what it is having, it may be, right, and it will come and attain another equilibrium position, right. That means, this was a one equilibrium position, it has come to the another equilibrium position, and then we call this as a basically neutral equilibrium, because it has assumed a new position, right, when subjected to disturbances, right. And we do also experience similar kind of things in our life. For example, you were very much happy with your family when you were doing your work in your family. Now, you have come over here, you are now in a stable position in this institute at this moment, right. Maybe after finishing your course, you will go and do a job or some other thing, you will be also again stable neutral position you will get, right, yes or no. So, this is a neutral position, but if you look at come back to this stable position, when we can call, because when it will be a large disturbances are there, then it is call it as a stable position, right. So, let us look at the another case where if it is ball is there in this kind of a surface, like let us say in a mountain or something like that or hill, and there is a you might have seen sometimes when you might have watched a mountain, there is a stone which is lying in a very big stone on the top, and then you might be thinking why it is not falling down, and if it will fall down what will happen, particularly when you go to the Himalayan region, you may find similar things. I had a similar experience. I was thinking why, if it will fall what will happen. So, if there is a little bit disturbances here, right, if there is a little bit distances, what will happen? The ball will roll down and it will not come back to its original position, whatever it is having, right. So, never returns back to its original position once it is disturbed, right. So, that happens also with our day to day lifestyle now, we are becoming irritated for a smaller things, right. And like this is a position which should be avoided. So, let us look at another case like a which is having a what you call, if the ball is in this position, right, and there is a change, little bit changes here. Let us say if the ball is here and then it can return back to the original position, but if the ball is the position is being changed to here, what will happen? It may be little bit stable, but however, if we will go over here, it is going down, it is becoming similar to the unstable equilibrium kind of things. That means, if there is a small change, it can manage, right, it can come back to its original position, right. But if it is subjected to a large change, right, then it cannot really return back to its original position, that is known as metastable positions. If you look at like in a phase change, lot of metastable positions do take place, like we will be discussing about phase change, then we will know particularly you can have subcooled liquid even at a what you call little higher pressure, right. And there is a also what you call, there are several like iron like which will be in cementite or in a metastable that can remain for years together. And if you look at your glass, glass also is in metastable, if it is a little bit jerk, it can break and other things, not like toughened glass like other glasses. So, that will be metastable, and this metastable also we do experience, particularly the people who get a very shock, for example, some people get heart attack, right. Whenever the shock is very severe due to some reason psychological or emotional or other things setback, they may collapse. So, that is also considered as a metal. They are stable all at the time, but small change they will not bother, but if it is a big shock kind of thing will happen in their life, they may be emotionally imbalanced. So, that we can call it as a metastable situations. So, however, we will restrict our discussion to the stable equilibrium systems only, and maybe I will be discussing little bit about the metastable when equilibrium, when we will be discussing about phase change processes. So, now let us look at the, because we will be looking at the what you call process and cycles in thermodynamic systems, because the thermodynamic systems are in the state of equilibrium, right. And if you look at the process, is basically will be taken by whenever a system is interacting with its surrounding. So, what will happen? It will go from one thermodynamic equilibrium state to another thermodynamic equilibrium state, right. And then that has to be basically state is known as what you call change in the equilibrium position, one position to another during is known as a process. So, let us consider our what you call piston and cylinder, and it contains some gas, and this we call it as a basically system boundary kind of things. If there is a small change in pressure, what will happen? That system will move and attains a equilibrium position, right. The piston will move in this way, and it will attain a equilibrium position. For example, let us say that you are at state 1 at this point, right. And suppose you change a position, as I told, there is a small tiny pressure change and then it is moving, then what will happen? It will come to the position A, and if you go on changing this pressure by a small amount, so what will happen? This will be this gas molecule which will be nearby, and like you will be try to resist this motion, and as a result there will be a pressure will be increasing in this point, because it is being compressed, right. And you will attain another state B, and you go on attaining these various states as you change this pressure on the other side of the piston. So, the point you will be moving in this point like that, and you attain a state 2. If I join this each position of the system as it goes, and that we call it as a path, or we call it as a process path. That means, a series of state through which a system undergoes during a process, we call it as a what you call system path. This we call it as a systems process path. Basically, this path is taken during the process. Now, let us look at, like, when a system returns back to its original state. Let us say you are here at station 1 and you are moving through this path during the what you call interaction of system with its surrounding, and then you reach a state 2 here, and you can return back to this path to the state 1, right, to another path, or you can return back with the same path, or we can take another path here and come back here. So, this we call it as a cycle. In the cycle, if you look at, that means it will be not depend on the path, am I right? It will be, it does not depend, if it is coming back, this is a cycle, right. So, this is a point, and it will be depend on the two state. But of course, if you look at the work done and other things, energy interaction will be different for different cycle, whatever you do. But in case of a path, if you want to define a process path, this is my process path, right, 1 to 2 and this is another process path. Now, this if I want to define the process path, what I need? I should know the state 1, I should know the state 2 and also I should know the path taken by the system, right. But whereas the cycle we always bother about the 2 state between which it will be, of course, it can take a different path. So, on a completion of cycle all system properties return to its original value, that is the meaning what I was telling. That means, if it has returned back following a cycle path, the properties will be same as that when it was started, but for this for the process path it need not to. So, to describe a process completely, I am just repeating again, it is important to specify the initial state and the final state of the process as well as the path and its interaction with a surrounding, right. So, this is very important when you describe a process completely, right. That means, what you need? You need to know the initial path, right, and you need to know the final path and also the what you call the path taken by the system during its interaction with the surrounding, one should know. So, when in the thermodynamics we will be looking at what you call a quasi static or quasi equilibrium process, right. Quasi sense it will be basically very slow manner or the change is not very much high. Suppose we will take this example, right, of our same piston and cylinder arrangement where the gas will be containing in this at a pressure P 1 and V 1, right. Of course, there is a lot of weights are here which is being balanced by this gas pressure P 1 and it is in equilibrium at the state 1, right. And this you can say that let us say 1 kilograms of the weight is there, let us say, and then what I happen? I will change what you call I will remove from here this weight blocks maybe something like 5 grams, right. Is very small as compared to 1 kilo. 1 kilo means what? Like 1 kg of force, am I right? 1 kg into this. So, and what will happen then? Of course, I am assuming the friction between the cylinder, this is my cylinder, right, and this is piston. The friction between piston and cylinder is what? Is not there, is 0. That means, there is no friction between piston and cylinder, which is not true in practical situation, am I right? Can you have a piston cylinder without any friction? Certainly no, right. But however, you can minimize it. Let us say we are assuming it to be 0, then what will happen? This is a tiny mass which you have removed and as a result the pressure will change here. That means, pressure acting by the weighing blocks will change and there will be little bit increase in the what you call pressure P A and volume will increase. Okay. And similarly, you remove this another maybe tiny block from here and then it will attain the P 2 and V 2 where P 2 is much lower than the P 1. You might have gone through several of them which I have not shown here and it has reached a V 2 position or the volume is increasing. So, if you look at this is happening in a very small gradient, a small differential here. As a result, that the process is taking place in a slower manner and which allow the system to maintain the equilibrium all the time, right. It is not suddenly like you are giving. That means, maintaining equilibrium all the time means what? That means, if there is a change in pressure in the gas of the system, that pressure P will be uniform across the all the time in the system, right. The change is not like here only the pressure will be higher and then the pressure will be different, other away from the piston. It is not that way. So, it is uniform all the time, and that process is known as quasi-static process, and in classical thermodynamic we will be assuming that it is all the time is in quasi equilibrium position. So, you might be thinking why we are emphasizing on that, right. Why we are emphasizing that it should be quasi equilibrium? Because of fact that suppose you are at state 1 and there is a tiny change and then you are coming to state A kind of things, right, or this position, and then if I will again put back that tiny weight which I had removed, then it can go back to the state 1. Okay. But if it is too much, it cannot. So, I mean like kind of things it can happen. So, and this process is a very very slow process and we call it this thing. As a result, we can change the direction of the process from this to that or from this to that in a slower manner by changing the pressure or changing the this thing, whatever the gradient is there. In this example, it is the pressure, it may be in temperature, it might be in concentration gradient, depending on that. So, infinitesimally very small amount, right. Then a process can be reversible, right. But let me tell you, it is hypothetically situations. However, you in practical problems won't be, it will be friction will be there will be you cannot have slow process, such a slow process, then people won't look at. But however, when we are analyze we can, and some of the process can be similar to this, it is not same. Okay. So, therefore, we will be in classical thermodynamic, we will be using the quasi equilibrium concept very often, right. Is that clear? Because this is a very important concept, which is the backbone of the classical thermodynamic, the quasi equilibrium concept, okay, process. So, therefore, that means what we are calling a reversible process when system and its surrounding return back to its initial state, right, wherever it was there, whenever system is interacting with surrounding, there will be some change in the system and also its surrounding, and if you reverse it back, both changes will be nullified, it will return back to its original position. We call it as a reversible process. That means, the process should be quasi-static or quasi equilibrium. All reversible process must be quasi-static, but all quasi-static process need not to be reversible. Are you getting this point? That means, like it may be a slow process, but however, if it is not returning back to its original position by changing or reversing it, such that system and surrounding are not returning back to its initial state, we cannot call it as a reversible, although the process is slow. Okay. So, however, all natural processes are irreversible. Okay. In engineering, we try to make as reversible as possible, but however, it will be impossible to eliminate the what you call frictional, so that it can be reversible fully, it is not possible, right. And during certain process, some properties may remain constant, right, which will be the might be having practical implication also, like those properties, those processes we can define in different ways, which you might be aware. If the temperature is remaining constant, what do we call that process? Isothermal. If pressure remaining constant, we call it as a isobaric process. If the volume is remaining constant, then we call it as a isochoric process. And if it is adiabatic, that means there is no heat transfer between system and surrounding, and also it is reversible, right, then we call it as an isentropic process, right. So, these are the processes which we will be discussing very often, now and often, and we will be using these processes by mimicking the natural processes or in actual cycles. What will be? We will be idealizing and then doing that. Of course, in some situation it may mimic the constant pressure process, right, or isothermal process kind of things. So, I will stop over here, right, and then we will continue in the next lecture.